You are all welcome to another beautiful session of our lecture videos on algebra, and today I'm looking at sets, that is of unit 3. Again, as usual, I'll go with my write-up and my slides. So we are looking at introduction to sets, the rules of sets or the rules of the game, and some examples. And at the end, we'll have the problem of the day. So let's quickly start with the introduction. We want to know what a set is. If you look at the definition I have in my slide 2, it says if n is a positive integer and the same n is not a square number, then the square root of the n is a set. It feels like a lot, but there are some keywords we want to look at for an integer. What is an integer? An integer, we know, are natural numbers on the real line. So -1, -2, 0, 1, 2, on and on, 3 dots before, 3 dots after. These are integers. So mathematically, we have a symbol like z to represent integers. We also have another word called a square number. What is a square number? A number that can be squared. So like 4 can be squared like 2 to the power 2. I think 9 can also be a squared number, like 3 square. 16 can be 4 square, and so on and so forth. So they are also integers, but they are squared. You can have a number to the power 2 to represent them. Or let me say n to the power 2. Okay. But then the peculiar thing is a positive integer. It means that we want them as counting. So 0, 1, 2, 3, and so on and so forth. These are the positive integers. I think sometimes we want to even ignore the 0 and start from 1. Yeah. So these are positive integers because 0 is neither negative or positive. Well, you can argue out. So these are the positive integers. So if there's nothing squared to represent 1, then it's a set. If there's nothing squared to represent 2, then it's a set. And that is the interpretation we are giving here. So let's take an examples. Verify which of these are sets and which of these are not sets. Root 2 is a set because 1 is a positive integer 2. And I can't have a number squared to get 2. That is not possible. I can't have this. 13 is a positive integer. I can't have the square of it. 99 is a positive integer. 201 is a positive integer. I can't have anything squared to represent it. So these are sets. Now let's come to the second argument. 16, someone will say, yes, this is a positive integer. So we mostly use z prime. This is a positive integer. But you realize that I can have something squared to represent it. And what is that? It is 4. So I can have, this is square root of 4 squared, which cancels out the square root and I get 4. It's no more a set. The second example, what is under the square root is not an integer, it's a fraction. And with our definitions, we don't expect a fraction, we expect integers which are positive. And so this is not a set. When I come to the third one, I have a square root of decimal points. These are all on the raw line, but they are not integers and they are not positive integers. So I don't even move to the squared aspect, but just them violating the rule of being a positive integer is enough to say that, hey, these guys are not sets. I hope that is clear enough. Okay, let's look at the rules of the game. There are things we want to take note of. Look at what we have here. We are adding 2 sets, but they have a common set here. So I can factorize this out. So these are basic mathematics. If I factorize out, then I can simply write my rule as this. Now the second rule, because they are all under the set, I can bring them in within the set. This is on its own, this on its own, but because they are all sets, I can rewrite them as the bigger square root and then the a and b under it. This implies that if b is equal to a, as we see here, then I'll have the square root of a squared, and then that becomes a. We know this. So that is the third rule. The fourth rule, there's no common factor here as we did in the first case, but because there's a multiplication here, I can bring the coefficients out, AC, and then multiply the sets. If I want to apply the rule here that says that if two sets are multiplying, I can bring them under the bigger umbrella, and that will be my answer. Okay, the fourth rule, if I have two sets dividing each other, I can take a bigger umbrella or a bigger set and then divide it, and that is it. These are simple rules. Now if I want to take the last two rules, we have a term called rationalization. You take your time pronouncing it. Rationalization, what does it mean and what does it do? I will not go details here, but we'll come across it in the subsequent slides. What do you see here against what is here? You realize that both the numerator and then the denominator has been multiplied by the square root of the b. Okay, so with the roots, I can have a bigger umbrella of ab over a bigger umbrella of b squared, and that gives me ab over b. You see, something has happened. The denominator has been cleared of its radical, of its said property. Okay, now look at the second one again. I still multiplied whatever denominator by the whole argument again, and what would I get? I get a root b over root b squared, which gives me a root b over b. Again, the denominator has been cleared of its set property or its radical position, and that is the interesting thing with rationalization. We multiply the whole argument by the let me not go there. Let me just stay within my field. Now look at this third example. Can I rationalize it? No. Why? Because the denominator b has no set on it. It is just b. So I can't say the square root of a over b times b over b. Even with this, it still cancels out. So we can perform rationalization when the denominator is not in a set form. I hope that is well understood. Okay, so that is a rule. Now let's go to applying our rules here. That are the examples. I think that will end on my slide 4. Examples here. I know you can use calculator to do these things, which is fine. If I want to find the square root of 8, this is a set because 1 is a positive integer, z plus, and then I can't have anything squared to represent it. But I can have two numbers multiplied. And by property, I have root 4 times root 2. I can split this up, and this gives me 2 root 2. You can simply see that. Because the square root of 4 is 2. The same way in the second example, so example 1, example 2, I can express 720 in these two forms. So I have 144 times root of 5. The 144 is 12. I'm not so sure. Okay. Then the third example, root 32, I can express as this one's root 8. I've already found root 8 here. So I simply bring it here. 2 root 2. This gives me 4 root 2 plus 2 root 2. Why is it 4? Because 16 is the square root. 4 square. Can I simplify this further? Yes. Because the sets are the same, I can add them to get 6 root 2. Properties of the set, we've used it. Now, let's come back to the real guy, the rationalization I talked about. So question 1 says, a set such as that cannot be simplified because the denominator has no roots on it. It is not a set. But look at number 2. I can rationalize it because this denominator is of interest here. Times 3 times root 3. And I'll get 2 root 3 over 3. If I multiply this, guys, it becomes square. So we cleared the denominator of 8 radical positions. So it says that the process of removing the radical form, that is the square root, from the denominator is rationalization, which we've already gone through here. At the end of the day, from root b we had simply b. From root b we had simply b. So we've done something to the denominator. Interestingly, someone will say, how do I do that? We use what we call the conjugate. We find the conjugate of it. It will not always be a single number. Your denominator can appear in any form as like 6. The important thing is look at the sign. If it's a positive, the conjugate becomes negative. If it's a negative, the conjugate becomes a positive. And this helps us with the rationalization. Hence, the conjugate has something to do with rationalization. You can't rationalize if you don't find the conjugate. At the end of the day, we are going to clear out the set or the radical. It is interesting to note that if I multiply 2 conjugates, it is no more a set. Like like slide 7. That is equation 1 and equation 2. You can try that out. When you multiply the conjugate, so a plus root b, its conjugate becomes a minus root b. Or if I have root a minus b, its conjugate becomes root a plus b. If I multiply them, it clears the set. Okay. So there's a smart quiz here. It says which would be the first step to rationalize, A, B, C, D. I'm not so sure the answer is, but you can check it out and then tell me what the answer would be. We have denominator. Don't forget, rationalization is on the denominator, not the numerator. So I have 1 plus root 2. The conjugate of this simply is 1 minus root 2. So which one do you think the answer would be? Where do I see 1 minus root 2? It is in B. And so the answer is B. Sorry. Now there's more to go. We have a question here to solve. It says simplify the given set in a form where P and Q are rational numbers. Now you would want to know what rational numbers are. But let's look at how you can work through this. This is the problem given. Because of the denominator, if I want to simplify this, I have to rationalize the denominator. And what do? You first find the conjugate. Because it's negative, it becomes a positive number. And then I multiply through, both up and down by it. And so that is what I have done here. Probably this might seem confusing. If I take away the cross sign, this is exactly what I have. And you can simplify further. This is expansion. You expand the bracket and then you are good to go. So check it out and then see the answer in slide 9. Work it out and confirm. Okay. Now to the last thing, that is the problem of the day. What are we working on? Again, I would always stress on this. When you see the word problem, you take your time, you read, you make extractions, and then you solve. So let's look at A. A says we are looking at some molar concentration of a certain compound in a solution. The solution is given. It says express the concentration in a certain form, where C is a positive integer, positive constant. So the problem is working on a molar concentration. It has given me the value of it, and it's requesting me, so I've done the extraction here. Now the problem is to find this in a certain form as C root 5. This means that I would want to find the square root of some two numbers, C times A, such that I can split this up as root C times root A, but A is 5. So what is root C? Look at what we want. We don't want root C, but we want a constant. It means that this root C should be something that can be, let me use B squared. So when it cancels out, then you get the B. So it must be a square number. If it's not a squared number, you can't find C. And so I don't know what that one is. You have to find it yourself. I've given you a clue of how the C should be. So you can leave your answer in the comment section. Okay. The second problem, that is B. We are looking at a biomedical reaction. So that is the experiment. I'm doing my extractions. It says this chemical reaction occurs in a rectangular vessel. There's some shape given, rectangular. This rectangular vessel has a length of that given. It has an area given as this. What do I want, or what else am I given? I want to find the width of, this is the problem I want to solve. I want to find the width of the vessel, of the rectangular vessel. But I said don't just find it. Leave it in this form. And there's a condition attached to it where P and Q are integers. Now I've already explained what integers are. So I don't expect, what's it? I don't expect, okay. Over here, we're not whether they are positive. It means we can expect negative numbers, but we don't want fractions. They are integers, so they must be whole numbers. So I expect to be -1, -2, or +1, +2. This is what I want. So let's look at the solutions here. First, I want to draw my rectangular shape. If you don't know what a rectangular shape looks like, this is what I have. To find the area of a rectangular shape, it is the length times breadth, or the width. But A is given, L is given. So to find B, by change of subject, let me use green, I can find B in this form by change of subject. And that is all I have to do. Now A is given as root 80, B is given as that. You realize that the second depends on the first argument, where you were asked to find root 80 in some form, some C root 5. So if you found a C, you are good to go. If your C is wrong, the entire problem is wrong. But we've all been students before. We are smart enough. Our workout might be wrong, but our final answer will never be wrong. So assuming I found my 80 to be C root 5, and I can conclude on this guy. The next step, I'm not done because it is not of the form I want. I have to rationalize it. And how do I do that? I find the conjugate of the denominator. The conjugate becomes 1 minus root 5, and I multiply it through. Again, if you take this cross away, we are just simply multiplying this. and then you continue. I expand here, so after simplifying I expand. If you expand, forgive me, I'm not writing the final answers. I'll get C 5C here. You can flow with me, and this multiplies that gives me this multiplying that gives me what I have here. If I take the denominator part here, I'll end up with -5. Please confirm if my workout is correct. Other than that, we are in trouble. Okay, so I can just divide through by -5. I'm splitting. What I'm doing here is to split because of the divisor. So there's some 5C over 5 here, and that's it. Are we done? We want a form as this, and so you want to rewrite it out. 5C over C, I get C because 5 over 5 cancels out, minus this on 5. It means that my P is this, my Q is that, and they must be integers. I expect that my C will be divisible by 5. Other than that, I'm going to get fraction. P and Q are integers, so you realize that we need a C to be a good answer or a correct answer. So kindly, if you work it out, let's express our answers in the comment section and see what we had. So P and then Q. All right, this brings me to the end of my set, and then the next will be on tricks. Thank you.